This is a Module 3 video describing other specific examples of electrophilic aromatic substitution reactions and their mechanisms. The four examples that are depicted in the final pages of this worksheet follow the same mechanism for the reaction of benzene with the electrophile. The difference is in the generation of the reactive electrophile. The mechanism that has been generally accepted for acylation, which was first reported by the European chemist Charles Friedel, working with an American chemist, James Crafts, reacts an acyl halide with a Lewis acid such as aluminum trichloride. The generally accepted mechanism involves an acylium ion intermediate. But there is another possible mechanism to consider, and that involves the nucleophilic addition of the electronegative oxygen to aluminum trichloride. In the class, we'll discuss the pros and cons of these two reactive intermediates, both of which are electrophiles that could potentially react with benzene. Turning to the next page of the worksheet, the alkylation of benzene can also be accomplished from alkyl halides upon activation with aluminum trichloride. This transformation was also discovered by Friedel and Crafts. As the chloride is the only atom in tertiary butyl chloride with non-bonded electron pairs, the mechanistic proposal is that a non-bonded pair of electrons on chlorine donates electrons to an empty orbital on the Lewis acid aluminum trichloride, and this leads to the formation of a carbocation and aluminum tetrachloride anion. This reaction works best when the carbocation has more stability as a tertiary carbocation or with resonance delocalization of positive charge. The principal support for the carbocation mechanism comes from the fact that you can get the same products by using other methods to generate the tertiary carbocation, such as protonation of isobutene with an acid that has a non-nucleophilic counteranion, such as hydrogen fluoride. In this case, the trick is to use a minimum amount of hydrogen fluoride as a catalyst so that the concentration of fluoride anion is low. If this is done in the presence of excess benzene, the concentration of benzene is higher than the concentration of fluoride anion, and therefore benzene is more likely to react with the cation than fluoride. Turning to the next page of the worksheet, the nitration of benzene is one of the commercially most important ways of introducing nitrogen onto an aromatic ring. The classical nitration uses nitric acid in the presence of a catalytic amount of sulfuric acid. The accepted mechanism requires generation of a nitronium ion with elimination of water. In the class meeting, we'll discuss three possible pathways in which nitric acid can react with sulfuric acid, which pathway gives nitronium ion plus water. Turning to the last page of the worksheet, this describes preparing the active electrophile for sulfonation. And for sulfonation, we use what is called fuming sulfuric acid, which is sulfuric acid with additional sulfur trioxide gas dissolved within it. That's an extremely acidic and electrophilic source of sulfur trioxide. Protonation of any of the three oxygens of sulfur trioxide gives the protonated sulfur trioxide cation, which accepts electrons from benzene in the typical electrophilic aromatic substitution mechanism. This concludes the Module 3 video on other specific examples of electrophilic aromatic substitution reactions.